this is one wing of this Kale lab. Like I said. So this has most of our liquid chromatography mass specs. This one is new Shimadzu QTOF, so it does high resolution. You can do non-targeted type analysis. So if you're looking for things beyond your 3D PFAS that you know you're looking for, if you want to look for more PFAS, or if you're looking at a completely different sample that's in liquid, water, etc., and you want to look for more things, this is an instrument that can do that for you. But how it does that is with exact mass measurements. You can actually assign what the formula is to the ion mass that's measured, unlike like a triple quad, where it's nominal mass, right? So it's just, they'll tell you mass at 400, or if you're super lucky, 400.1. That's not enough accuracy to assign up the formula. Whereas this one and that one, which is even better over there, can give you a mass of 400.1562. And then that is enough accuracy to actually assign the formula to it without anything else. There's a lot of caveats and things to consider with that. But luckily, in case you ever are curious about it, that is what like most of us here have been trained in our entire PhD careers and past. So we can definitely help you with any non-targeted analysis you might be curious about going into the future.
Thank you so much.
You say this one can distinguish between different types of PFAS in water?
Oh yeah, I mean most of them can, because the PFAS themselves are separated enough by mass. What I mean is, like with a nominal mass, like your standard GC, MS, low resolution mass spec type thing. Of course, my marker doesn't work. That's a shame. The PhD students. He's a chemistry PhD student who's working in the lab this semester, and we'll be trying to keep him around just because he's very helpful to have around to do stuff.
Maybe we should take him to El Paso.
Oh yeah.
If you want to give him a postdoc, he's got a couple more years on his PhD, but so anyway, with low resolution, you would have, say, this is 399, 400, 401, and you would have a peak here, here, and here on low resolution. You would just see basically 400. Whereas with higher resolution, like what this one's capable of, let's just focus on 400 here, you would see something more like, they're not necessarily that pattern, but you would see a bunch of different masses that you can assign. So all of these masses are inside of this peak. Mm-hmm. And so that's what I mean by the high resolution, and be able to identify things that you aren't necessarily looking for. If you're looking just at PFAS, like PFOA and PFHXS, or something like that, XA, they're going to be completely different masses, right? Mm-hmm. PFOA is at 398, XA is going to be at like whatever C minus CF2 is.
So it's definitely good for distinguish between a long chain and short chain. Not for long chain be the same the number of the carbon, if not good, right?
It would actually be really good for the same number of carbons potentially. So
with different type of the functional groups, it can still.
If you can ionize it, you can separate it. You can see it.
Depends on the stationary phase we are using.
Yeah, so it depends. Yeah, it depends on what's in your sample. So if your stationary phase, because you don't with the columns. So that's, I'm trying to make sure so with the LC system, you have a column.
Okay.
And so with low resolution or just column in general, you would put your PFAS in there, and we'll simplify it, your C8 will stick a little bit better than your C6, will stick a little better than your C4, right? So the C4 would come off first, C6, C8, generally. I mean, it depends on the polarity of the functional groups, et cetera, et cetera. But for the mass spec itself, it can separate those masses without chromatography. It's just, you ionize those masses, and then what this is a quadrupole coupled TOF, so time of flight mass spec. And so a time of flight mass spec, basically all your ions molecules get ionized, they come into the instrument, and then they get accelerated with an equivalent charge. I can draw this too. But here's a very, very simple time of flight mass spec. And so this is your flight tube. This whole thing right here, this is your flight tube. And to super simplify, it's not exactly how it works, but let's say all your ions are floating around right here. And there's some that are bigger and some that are smaller, and some, all that, right?
Sorry, before if our PFAS is not polar, polar or what?
So most PFAS gets ionized in negative mode.
Oh, so you can ionize them?
Oh yeah. Oh yeah, they get ionized. They're really, so the last one we're called carboxylic acid, right? So you have your PFOA is C8 carboxylic acid. That carboxylic acid ionizes beautifully. It just ionizes right off the top, and there's no issue with that. Same with like the sulfonate. And with a low resolution, like nominal resolution instrument like the QTOF, and it has a specific geometry of quadrupole. So you know what a quadrupole is?
Yeah, maybe they know.
Four rods kind of.
Four rods, yeah, that's exactly what it is. So it's exactly what it sounds like. It's four rods that they apply charges to in alternating patterns, basically. And depending on the intensity and the voltages of those charges being applied, it separates out ions. And so it'll be tuned to do, and what it does actually is it does one ion at a time. So it'll do 100, 101, 102, 103, 104, and it'll kick everything else out based on how it gets tuned along the way. Of course, that's really, really fast, so you still get everything. And this one has the capacity to do NMSU fragmentation because first off, we ionize it with electric spray ionization, which is the soft ionization. It doesn't blow things up. This is not supposed to. No, we use electric spray, so it's just liquid, and you apply a voltage to the liquid. Let's see, I'll show it a little bit here. This is a different version of it. This is a nano flow. So it's really, really low flow rate. It flows at like 300 nanoliters a minute. And so you see that little needle? You can see like the droplet coming off the needle there. So that needle has a charge applied to it, which then gets transferred to the liquid as it comes through, and it explodes out basically into a spray. And then that charge sits on the droplets, because it spits out droplets, and there's charge on the surface of those droplets. The simplest way of explaining it, it's not necessarily completely accurate, but the simplest way of explaining it is the solvent will kind of evaporate, and the charge will then be stuck to the molecule of your interest, and now it's ionized. That's not exactly how it works. There's still actually, last I knew, there was still discussion about exactly how it works, but that's the most intuitive way, I think, to think about it. I'm just showing that, so you can tweak them and get everything lined up properly. This window is often showing this, so it's showing our actual mass collections. This can show like our LC program. This is a Waters system because we have that means a Waters LC. But we can put that, or we can put the like setting up a sequence type of stuff. It's just nice to have everything more readily available. Yeah, we got Tanner here too. I imagine you want often you want to keep it cold. And so it'll do an auto sampler, it'll take a vial, it'll do an injection on a vial, send it through, it'll go through a bunch of pumps, send it through the column, and then it gets separated on the column, right? Because some things will stick better than others to the column and they'll get dragged along. Mostly polarity. A little mass can play a bit of a role, but this is a C18 column, And so if it's something that's very polar, means it's really soluble in water, it'll just spit right through. Whereas if it's non-polar, it'll stick a little bit better because it's largely C18, so carbon 18 is the material in there, with a few little tweaks and add-ons. And so it'll separate all the way. Things that are more non-polar will stick to it, and they'll take a higher amount of organic, oftentimes asexual system. It uses CO2 as one of its solvents, one of its things, as opposed to a normal LC system which uses water and methanol, for example. This one will use supercritical CO2, so you're getting CO2 into a quasi-liquid state, right, at a supercritical point, and then it separates through a column, and it is a greener way of doing things. I mean, it does generate less waste, it generates CO2, which has its own set of issues, but...
Sorry to ask you, I have no...
Triple quad. See if geometry is a little bit different, but it has the ability to do... Right now it's doing a standard liquid injection, so it's going to pick up a microliter, and eventually it's going to move over to injection. Keep watching it. But we also have the option to do headspace analysis. So if you're looking for gas phase things, and I'll put them in a vial and you have a little bit of liquid or something, or if you just capture it, you can do gas phase injection. And we can also do SPEMI, which is solid phase micro extraction. And so it has a little, it's kind of like it's similar to a little really good for hydrocarbons, for your fatty acids. This is an instrument that we may set you up on if you want to come. We have not. It can be done. There are a few GC PFAS. They're not as common. I've looked into a couple of times, and there's a few things that are only available from GC. Most everything is just LC with PFAS. You get it. Even I think there's even some 100-meter columns if you really need to get something separated. It's really complex.
For this one, we don't have the working issue like LCMS.
No, you don't get clogged with this unless you're really screwing up. But you do get leaks. Leaks are a bigger issue with GC systems. Once they get tight, they generally all right. But that one right there yesterday, we've been using it, and apparently it's just getting through it. Typically, it's really used for gases. It's best used for gases. But it will detect anything, but it's not as sensitive as like the mass spec, and you don't get mass spec in. So it's our current operations for this thing. Kind of my idea is to use it as a pre-test for the mass spec, basically, and see if we can make something work. If we can detect it here, then we can definitely detect it over there. And if there's something that doesn't need to worry about concentration, we can just run it and go, basically. And then this one is the ECD. It has a radioisotope nickel detector thing in there, so it's radioactive. And what it does best is halogens. Halogens and I think like nitrogen a little bit. So in theory, if you could get your PFAS into the gas phase, this might be a really nice detector. Primarily, people do PCBs. PCBs is a big one. Polychlorinated biphenyls. That's right. So PCB is a pollutant from before time. It's still an issue, but people don't care about it as much anymore. But PCBs are really a primary thing that gets analyzed with these type of instruments.
And this equipment looks really new because they are touched, I suppose, you know.
They're all very new.
Yeah,
This one we haven't really used yet. Organic carbon or total nitrogen in a sample of some sort. This is what you can use. If it's in water, especially, you have it in water, and you need to know how much OC is in this sample. You run it; it'll tell you how much OC is in your sample, which it's primarily useful for environmental type studies. A lot of like water scientists do that kind of stuff. There's some things I want to do with it as well. I'd have to put my samples into water if I were to collect them, but that's all right.
Can I ask the
Mhm.
full name of TOC? Is it stand for?
It's just going to be total organic carbon.
Total organic carbon.
Yeah, total organic. I don't know what the L is, honestly, but probably liquid. Total organic carbon liquid. Whereas this module here is our solid sample module. So this one, if you have a solid sample, you want to look at soil, you want to look at something else, you can put it in here. And it just puts it, you put it into this little tray here, and then you push that tray into the oven. The oven's not on, we can't leave this one off because it's really hot. But you push it in the oven and it burns it all off, basically.
So what it will give you, the total carbon?
Total carbon, and so this one gives you the total carbon, this one gives you the inorganic carbon, and then between total carbon and inorganic carbon, whatever's left over, like you subtract the inorganic carbon from total carbon, that's your organic carbon.
And
Sorry,
So
the
go on.
signal is mass, yeah?
The signal, I mean, what it's detecting is CO2, really,
And
because
for
it's got
that
lasers
one?
basically. Yeah, it's the same thing for this one as well. It does. It's going to be effectively a resin over here, but it's going to be more for your polymers and trying to separate out polymers, separate long chain things, and tell how much of it do you have. It does have it has a refractive index detector and a photodiode array detector, so it has a couple detectors on it. And you put your sample in, it's filled through the gel instead of like your classic column. It's a gel column type of thing. It'll separate those things out, and you can detect them. So it's really good for super large polymers because it separates by size, basically. With this, it's a quasi. It's not quite the same as a quasi size exclusion kind of chromatography system. This is just gel permeation instead. And so you can put those really large polymers. If you don't need mass spec data, then this will still say, okay, we got it separated in 20 minutes, our thing of interest comes out, etc. This one is not a preparatory one. Like the other thing is preparatory, this is not preparatory. It just does the detection itself. But it can be of use as well for somebody